Okay, let's continue with this idea of the first derivative test. Once again, the first derivative test says if c is a critical number of f and the function is continuous, then those two things together will tell you that x equals c is either a local min or local max. Let's restate it again. If c is a critical number, that means a value x equals c where the derivative of f prime of c is either equal to 0 or does not exist. That would make it a critical number. And the function of the original f is continuous. Those two things together would imply that the x equals c is either a local min or a local max. Okay, so let's check out this problem or this interpretation of this idea. Here we're going to draw a continuous function. No holes, no cliffs, the ant can crawl over it. And look at this x equals c. It has a flat tangent on the curve, which means it's a value where the f prime of c is equal to 0. It's a critical number with a continuous function. So that we're assured by the first derivative test, this is going to be a local max. And sure enough, looking at the slope of the tangent on each side being positive and then negative makes it very clear we have a local max here. Here's another continuous function, no holes, no gaps. And here's another value, x equals c, that has a flat tangent, which means f prime of c equals 0. In other words, it's one of those critical numbers. Okay, continuous function, critical number, and it's really obvious here. In with these two conditions, you're going to have a positive and negative slope, opposite signs on each side of the x equals c, and it looks really clear from the picture. You're going to have a local min in this case. Check out this next example. X equals c. It does not have a flat tangent. So f prime of c is not 0, and it certainly exists there. You have a continuous function, but you don't have a critical number. Look what's happening to the tangent on each side. You get a tangent leaning to the right on both sides. It's so clear this is not a local extremity. You can just look at the graph and see that. Similarly, for this graph that's continuous, but x equals c is not a critical number. It doesn't have a 0 slope or a does not exist slope. And so you can see further when you look at the slope on each side of the tangent for x on the right and x on the left of c, you have this guy leaning in the same direction. There's no local extrema occurring in either of these two examples in the second row. Now, what I want you to do is consider this next example in conjunction with the first example at the top. In this situation, we have additionally, because relative min or relative max may exist where the function is not differentiable, you could imagine this situation that we're about to see. Now, I'm going to draw two pictures, and they're both going to be continuous functions. Continuous functions. Okay, look at here, x equals c. Oh, look at that. Oh, a cusp, a sharp turn. It's not differentiable at x equals c because there's a sharp turn. All right, that makes it a critical number. X equals c is a critical number because f prime of c doesn't exist. And so you can look at the slopes on each time just to verify. You've got a change in the sign of the slope on the left and the right. So it's really clear you've got yourself a local max here, even though we do not have a derivative at x equals c. Not important, was never an issue. It's the other qualification to be a critical number not to have a derivative there. Same thing when you put the cusp on the graph upside down. This x equals c doesn't have a 0 for f prime of c, but it does have a f prime of c does not exist, so it is a critical number, and then you further verify that this is going to work for this continuous function by just looking at the slope. I mean, you can tell by looking at the slope that this guy's coming down and it's going to be a local minimum even though the derivative at that point does not exist.